Okay, so get this. It's going to sound completely backwards, but what if I told you the safest planes in the sky are the ones that are literally engineered to fail? It's true. Modern aerospace isn't just about stopping things from breaking, it's about mastering the art of the break itself.
And that's the big paradox we're diving into today, isn't it? How on earth can planning for failure make a massive machine flying miles above the ground fundamentally safer? It just doesn't feel right, but trust me, it's the absolute foundation of modern aviation safety. And the answer is all wrapped up in this incredible concept, fail-safe design. Look, the goal isn't to build something that never breaks. That's just impossible. Instead, it's a whole philosophy where engineers design parts so that when they do fail, they do it in a totally predictable and controlled way. Think of it like this. If something's got to give, you want to be the one who decides how and when it gives. They use clever tricks like redundancy, having backup systems, and multiple load paths, so if one piece of the structure fails, its neighbors can just pick up the slack.
To really get this, let's look at how engineers design for failure against three of the biggest threats out there. And the first one? Well, it's the kind of thing that makes headlines. A sudden, violent impact.
So problem number one is kinetic impact. In the world of aviation, the classic and, let's be honest, pretty terrifying example of this is a bird strike. You might think it's just a bird, but a small bird hitting a jet engine moving at hundreds of miles per hour unleashes a mind-boggling amount of destructive energy. Now, engineers don't just guess about this stuff. They turn a chaotic event into cold, hard science. They calculate something called the critical impact parameter, or CIP. It's this incredibly precise formula that factors in the bird's weight, the plane's speed, and exactly where it hits to figure out the absolute worst-case scenario. It's all about quantifying the threat before you can design for it.
And here's where it gets really wild. This is how they actually test it. The FAA's bird ingestion test is absolutely brutal. They use that CIP calculation to set up the most damaging test they can. Then, they take a real, running engine and fire a simulated bird right into it. And here's the kicker. The engine doesn't have to work perfectly after, but what it cannot do is catch fire, and it absolutely positively cannot break off the plane. It's designed to fail, sure, but to fail safely.
Okay, so that's how we deal with a sudden, visible impact. But what about the threats you can't see? The second big challenge is the slow, creeping danger of metal fatigue.
Every single flight, the metal on a plane gets stressed over and over and over. Tiny cracks can form and just grow over time. That's fatigue. But not all breaks are created equal. A brittle fracture is an engineer's worst nightmare. It's fast, unpredictable, and completely catastrophic. The part just shatters. A ductile fracture, though, that's different. It's slow. The material actually stretches and deforms first, giving you a visible warning before it finally breaks. And on an airplane, a warning sign is everything. This is why choosing the right material is so incredibly important. Here, we're looking at the fatigue life for three common aluminum alloys used in planes. The numbers show the average number of stress cycles each can take before it's expected to fail. And you can see right away there are some pretty big differences.
Yeah, this bar chart makes it super clear. Alloy 7075 is the clear winner, right? It lasts the longest. So you might think, well, just build the whole plane out of that. But, and this is a huge but, engineers almost never just pick the strongest material. They might choose alloy 2024 because it has great all-around properties, or even the weaker 6061 if preventing corrosion is a bigger deal than raw strength in a certain spot. It's always a trade-off. It's about choosing the alloy that will fail in the most predictable, manageable way for that specific part.
All right, so we've covered sudden impacts and invisible stress. Let's talk about our third challenge, a force of nature with a power of 1,000,000 volts. We're talking about lightning. Now, this is a pretty modern problem. See, older planes were made of aluminum, which is an amazing electrical conductor. If lightning hit, the charge would just flow harmlessly over the metal skin and exit. No problem. But today's aircraft use a ton of lightweight composites, like carbon fiber, which are way less conductive. And that makes them a lot more vulnerable to damage from a lightning strike. And the difference is, well, it's dramatic. Look at this. On the left, that's an unprotected composite panel after a simulated lightning strike. It just blows a hole right through it. But on the right, that's a panel with a protective system built in. The energy is spread out, and the structural damage is almost nothing. So what is this magic solution?
It's an incredibly clever idea called expanded metal foil. Engineers take a super thin sheet of metal, usually copper, cut a bunch of tiny slits in it and then stretch it out into a fine mesh. This mesh becomes the outermost layer of the composite skin. And because it's one single connected piece, it can't unravel, and it gives you perfect electrical connectivity across the whole surface. It's a lightweight, super elegant solution to a massive electrical problem.
And just like with the bird strikes, they test the daylights out of this. In these high-voltage labs, engineers blast these components with man-made lightning to prove the protective systems work exactly like they're supposed to. Again and again, it's about anticipating the failure and engineering a safe path for all that destructive energy to go.
So when you put all these pieces together, you don't just have a few clever solutions. What you really have is a symphony of safety.
It's a complete integrated safety net. It starts with the whole fail-safe philosophy. Then comes the brutal, real-world testing. That's backed up by deep material science, choosing not just the strongest stuff, but the most predictable. And finally, you have these genius protective systems, like the conductive mesh layered right into the plane structure. Every single system is designed to manage failure.
But the work is never finished. This quote from an expert really hits the nail on the head. It's all a compromise, a constant balancing act. Every time new materials are developed, engineers have to figure out how they play with the old ones and how they might fail. They're always innovating, always looking for that next combination of solutions to make flying safer.
So the main takeaway is this. The safety of every single flight depends on thousands of hours from engineers whose entire job is to plan for things to go wrong. Which leaves us with one final thought, doesn't it? If they've already engineered solutions for the failures we know about today, what's the next invisible threat they're already designing for tomorrow?